This is the beginning of Lecture 17 Part 2. In Lecture 17 Part 1, we were investigating what leads to stratospheric ozone destruction. We looked at some natural sources and found out that the natural sources can explain the 8% decrease in the ozone concentration over the last 20 years. And so we had to look to some synthetic sources, some man-made chemical that has been introduced into the environment over the last 30 years or so. And the conclusion was that it's the CFCs that have been introduced. It's a new chemical that was very, very useful in allowing the growth of industry because it's a safe refrigerant. So it's used in refrigerators and air conditioning units. It's also used as a foaming agent in making plastics and other industrial processes. Not to mention even in hairspray, aerosol cans use CFCs too, because under pressure they're liquid, and then when the pressure is reduced they go to a gas, and they would carry, for example, hairspray across from the can to a person's head. So anyway, they got used pretty widespread in the modern economies over the last 30 years or so. So anyway, because of all these unique properties, that it's not toxic and it's very, very stable, the CFCs are also stable in the environment. You can breathe them in and breathe them out. They're not going to react with the other metabolites in your body or whatnot. And so because, for example, if you look at Freon 12, for example, or the CFC 12, that was the one that had 2 chlorines and 2 fluorines. And we noted that these bonds are very, very strong, so it's a very, very stable molecule. As a matter of fact, it's stable in the atmosphere, can be stable in the atmosphere, in the lower atmosphere, for up to 120 years. So that's a very, very stable molecule. And it takes about 5 years for this molecule, if it's released on the, at the ground level, it takes about 5 years for it to make it up to the stratosphere. Okay, to make its way up to the stratosphere. And I think you all know that, gas particles, gas molecules, and gas atoms move very, very fast. But every time a gas, molecule collides with another gas molecule, it's going to change direction. So these gases, they're bouncing all over the place, and eventually over time they'll make enough motion to get themselves out to the stratosphere, enough, if you will, forward motion. So anyway, it takes about 5 years. So they're very stable until they get into the stratosphere, and when they get into the stratosphere, they will actually break down in the presence of UVC radiation. Okay, it takes high energy ultraviolet radiation, but it is present in the upper atmosphere, and in the presence of that radiation, it's enough energy to break these very stable bonds, and the CCl bonds are stronger, so the bond that's broken in the presence of this UV radiation of less than 220 nanometers in wavelength, you end up with this. Okay, it's a very reactive, it's a free radical. This is left as a free radical, and then this chlorine is the bad guy. It's a very, very reactive atom. Remember, once the bond is broken, the free radical is short for the Lewis symbol, which is 7 electrons in its valence electron. We model it with just 1 dot, but that doesn't mean there's just 1 electron. That's the way we model free radicals, to indicate there's an unpaired electron. And unpaired electrons are very, very unstable. And so the actual atom that you've released into the upper atmosphere is a chlorine atom. And the chlorine atom is very, very reactive. Okay, so the Freon, although it's stable and good in the troposphere, once it gets up into the upper atmosphere, will react with high energy ultraviolet radiation, break the bond to form the chlorine atom.